All right, welcome, Julian. This is chapter 3, okay? In the last chapter, we're looking at electric field and we saw quite amazing things about electric field. Now we're in chapter 3 and we are to discuss Gauss Law, right? Good. So, chapter 3 is basically tag Gauss Law, and this chapter actually is divided into, do I call it two places now? Because I'm tempted to give it into two. First and foremost, application of Gauss law in plane surfaces and Gauss law in enclosed surfaces called Gaussian surface, right? I think basically that is what the chapter is all about. All about plane surfaces and Gaussian surfaces. So you're going to see different things, how the electric field generated by an infinitely long wire, by an infinitely large plate of positive charges. You're going to even see electric field generated by two plates. You're going to talk about the electric field generated by a charged particle enclosed in a Gaussian surface, usually spherical surface. You're going to notice that a cylindrical Gaussian surface holds no electric flux. A lot of things like that which we're going to discuss, but everything boils down to understanding the concept of flux from Michael Faraday's point of view of electric field. Now, this chapter is going to be discussing purely Gauss law. Now, unlike Coulomb's law that is focusing on force of electrostatic between two charges, Gauss law focuses on how to determine the magnitude of electric field generated by a particular charge, either within a surface or in an open plane. So what is the magnitude of electric field generated by a charge? That is what Gauss law is all about. As for Coulomb's law, he's interested in the force of attraction. Now we are interested in the magnitude of the field. You get it? So when you're talking about the magnitude of the field here, you have to be very careful because the quantity of charge, the sign of the charges are very, very sacrosanct. You don't neglect charges here. If you do, you're going to be in a hot soup, bro. You don't neglect charges here at all. So let's look at Gauss law. First, before we go into Gauss law itself, flux is a parameter that one cannot neglect in the concept of Gauss law. What is flux? Flux is simply the number of electric field lines that passes through a surface. If the number of field lines passing through a square surface are 100, that is the flux represented by flux. So the number of field lines passing through a surface is referred to as flux. The higher the number of field lines, the higher the flux. It's a direct proportionality. Flux is, however, measured in Newton meter square per coulomb. Yeah, Newton meter square per coulomb. And it is also important for you to know that flux can also be defined as the product of electric field and the surface area in contact with the material or with the field lines, as the case may be. So flux can either be the number of field lines entering a surface, or you can simply call it the product of electric field intensity times what? Times the area in contact. Now the area we're talking about in contact comes with a normal attached to it. A normal. And that normal is perpendicular to that area. That normal makes area a vector quantity. Ideally, area is not a vector quantity. But because of the presence of a normal to the area that is always perpendicular, it makes it a vector quantity. So if you say that flux is a product of electric field and area, then we all know that flux is a scalar quantity, right? Electric field is a vector quantity. So area here is as well a vector quantity because of the presence of the flux. Because if the flux is at 0 degrees to the field lines, then you have maximum flux. If the electric field is at an angle theta to field lines, you have a moderate flux. If the electric field is at 90 degrees to the normal, you have a minimum flux, approximately 0, if not 0. So the position of the plate determines the magnitude of the flux. And that makes area a vector quantity in this topic. So flux is the product of two vector quantities, electric field and area. Good. Now let's go a little bit into details. If, for example, I tilt a rectangular plate at an angle of theta, the theta we are talking about is the angle formed by the normal to the plate and the electric field lines. So the angle between the normal to the plate and the electric field lines is theta. So if you rule a line from the electric field line to hit the normal at an angle of 90 degrees, then you will discover that the electric field lines will now turn to become E cos theta. Yes, E cos theta on the direction of the electric field. And that simply means that flux can also be written as electric field times area times cos theta. The theta we are talking about is coming attached to the E. So it's actually E cos theta times the area. You get it? Good. So take good note of that. Now, it is also important for you to know that flux can either be positive or negative. When flux is positive, it simply means that you have the field lines radiating outward. When flux is negative, it means that you have field lines radiating inward, because charges that are negatively charged move inward, while those that are positively charged move outward, right? Now let's look at flux in an open surface. I'm going to give you 3 scenarios to get this done. 3 scenarios. I have a rectangular plate sheet that is just positioned at 90 degrees to electric field lines. Take note, when the rectangular surface is at 90 degrees to the field lines, flux is maximum. However, the direction of the normal to that rectangular plate is at 0 degrees to the field lines. And because it is at 0 degrees to the field lines, automatically at 0 degrees to the normal, electric flux is maximum. In as much as electric flux is maximum when it is at 90 degrees to the plate. So, but you have to be careful. It is 90 degrees to the plate, but 0 degrees to the normal. And that is where it is maximum. The reason is because by the time you have EA cos theta, if you substitute 0 in the place of theta, cos 0 degrees is 1. So 1 times EA is EA, so it's maximum at that point. If I decide to tilt this rectangular plate at an angle of theta between the normal and the electric field, then let's say the angle is 60 degrees. I'm going to get a moderate flux. In fact, the flux I'm going to get is half, because cos 60 degrees is a half. So a half of EA is what I'm going to get as the flux at that point. So it's not maximum, it's moderate. At this point, the angle between the normal and the field lines is less than 90, and greater than 0. Good. Now, if I decide to lie the flux horizontally, the rectangular plate horizontally, such that the field lines are at 0 degrees to the plate, but 90 degrees to the normal, what happens? Flux becomes minimum, because the plate will virtually absorb little or no field lines. The lines will just pass through by. So you have to be very careful with these 3 parameters, because they are sacrosanct. Next, we're going to be talking about is the flux in an enclosed surface. How do I calculate the magnitude of flux generated by a charge? Gauss Law came up with the concept of using a Gaussian surface. Now, when you have a Gaussian surface will help you calculate the magnitude of flux generated by a charge within that surface. And of course, a Gaussian surface will come with multiple holes, very, very tiny holes around it, whereby the field lines can either move outward or inward depending on the charge within that Gaussian surface. However, if you have a positive charge within a Gaussian surface, you will discover that the field lines will be radiating outside. If you have a negative charge within the Gaussian surface, the field lines will be radiating towards the inside. If, however, you have more of the positive charges than the negative charges within a Gaussian surface, that means more of the field lines will be leaving the surface than entering the surface. And that flux is positive, because more is leaving, meaning that there's more of positive charges. If, however, in a Gaussian surface, more field lines are entering than the field lines leaving, then that particular Gaussian surface has a negative charge, which is in majority from the inside. Hence, the flux is declared negative. Now, what of a scenario whereby the number of positive charges happens to be equal to the number of negative charges within a Gaussian surface. That becomes another topic which you have to understand. And this is simply because at that point in time, the number of fluid lines leaving the surface becomes equal to the number of fluid lines entering the surface. And on that note, flux becomes zero. It is no longer positive, neither is it now negative. At that point, it becomes zero. Now the big question is, how do we calculate the magnitude of the flux? It is one thing to know it's positive or negative. It's another thing to know if it is zero whatsoever. How do you now calculate the magnitude of the flux? In calculating the magnitude of the flux generated by a charge within a Gaussian surface, the concept of closed surface integral is very sacrosanct. In fact, for a matter of fact, flux is equal to the closed surface integral of the electric field generated by the charge dA. The dA we are talking about is the small area through which the fluid lines are living on the Gaussian surface. So there are multiple of them. So when you say the closed surface integral, you're not integrating all the small surfaces through which the fluid lines are living or entering the Gaussian surface. So by the time you find the integral of that parameter, you will still end up with flux equals to EA. So if, for example, I'm using a spherical object as my Gaussian surface and I have a quantity of charge within, let's say a positive charge, for example. Now, what will be the quantity of flux generated by that charge within that surface? It is simply going to be equal to 4 pi kq. Now, the big question is, how did you get to this figure? Simple. If I put a charge within a Gaussian surface, and that surface happens to be a sphere that is spherical, the area of that surface becomes 4 pi r squared because that is the area of a sphere. Good. So if I apply the law of flux, which is flux equals to the closed surface integral of the electric field dA, electric field is a constant dA. If I integrate dA, I'm going to get A, right? So A there stands for 4 pi r squared. So I'm going to have flux being equals to E 4 pi r squared. And I also know that electric field is equal to kq over r squared. That's electric field intensity. Electric field intensity is kq over r squared. So substitute that, and then you discover that the r squared will cancel each other, and then you'll be left with 4 pi kq. And this formula simply tells you that the magnitude of the flux generated within a Gaussian surface is independent of what? The radius of the Gaussian surface. The radius of the Gaussian surface has no role to play. What plays the major role here is the magnitude of the charge, and that is the value of Q. If, however, from this formula, I want to go further, flux is equal to 4 pi kq. I will ask myself the question, but from this formula, k is equal to 1 all over 4 pi epsilon naught in free space. Substitute that as 1 all over 4 pi epsilon naught in that formula of 4 pi kq, and you will discover that flux becomes q over E naught because 4 pi will cancel each other. And when that happens, this is where Gauss Law came into play. And then when Gauss Law discovered this formula, he made a public statement, a public declaration of his law, saying that the total electric flux through an enclosed surface is equal to the net quantity of charge. Take note, is equal to the net quantity of charge in the surface divided by the permittivity of free space. In other words, the net quantity of charge in an isolated system, in an enclosed system, in a Gaussian surface, it's simply, or the flux generated by a charge in a Gaussian surface is simply the ratio of the quantity of charge, which is the net quantity of charge, to the permittivity of free space. And that is why flux is equal to Q net all over E naught. And of course, when we say Q net, that means you can have multiple charges, okay? When the charges are so plenty that the number of positive equals to the number of negative, automatically there is no flux. And when the charges happen to have more positive than negative, then you have a positive sign, as the case may be. So that is very, very sacrosanct. So if flux is equal to Q all over E naught, when you know that the same flux is equal to EA, then you can calculate the electric field generated by that charge. You get it? So the electric field generated by a charge enclosed in a Gaussian surface is simply E equals to Q all over E naught A. How did I come about that? From Gauss Law. Gauss Law says that flux is equal to Q over E naught. That same flux is equal to EA. E is the electric field, A is the area. So make E the subject of the formula. You have the electric field generated by a charged particle within a Gaussian surface. Now, there are some very vital things you need to know about an electrical conductor. An electrical conductor that is in equilibrium simply means that the flux or the total positive and negative charges within that conductor is zero for it to be in equilibrium. That's the meaning. So the total number of positive charges and the total number of negative charges are equal. In other words, the electric field inside the solid conductor is equal to zero. That is when it is at equilibrium. However, also note that there can never be in any point of time excess charges within a conductor. So when a conductor happens to exceed equilibrium, that means you now have excess charges. Where will those excess charges reside? Within the conductor or outside the surface of the conductor? Definitely they will never reside within, but they will always reside outside that conductor. Very important point to remember. And then that takes us to Gaussian surface that is cylindrical. It is important for you to know that a cylindrical Gaussian surface holds no flux. No flux at all. In other words, when a uniform electric field is passed through a cylindrical Gaussian surface, the total flux held by that Gaussian cylinder is equal to zero. Now, how does this happen? A Gaussian cylinder has two hollow sides and then a surface. The electric field entering uniformly enters the first circle at an angle of 180 degrees to the normal of that surface. Then midway to it, it is 90 degrees to the surface of the Gaussian surface. Then at the end of the Gaussian surface, it becomes parallel to the normal. So when it is at 180, you have EA cos 180, which is already going to give you a minus EA, because 180 is 1, minus 1. Then at 90 degrees, it's going to be 0 because cos 90 degrees is 0. Then as it is leaving the surface, the Gaussian surface, it leaves parallel to the normal. That means it leaves at an angle of 0 degrees to the normal. And cos 0 degrees is plus 1. So minus EA plus EA will give you 0. So a Gaussian cylinder holds no flux. Very important. It is also important for you to know that the electric field generated by an infinitely long wire of charges is given by lambda all over 2 pi r epsilon naught. Lambda is the linear charge density, which is simply quantity of charge over L. And then 2 pi r simply represents the surface, the cylindrical circumference of the wire. Okay, r, there's the radius of the wire. Then epsilon naught is in free space. If, however, you are given relative permittivity, then that epsilon naught becomes er epsilon naught. So you're going to have lambda all over 2 pi r er epsilon naught. Now that takes us to the quantity of electric field generated by an infinitely large plate of positive charges. Just imagine I have an infinitely large plate of positive charges. I want to determine the quantity of electric field generated by this positive plate. All I need is a Gaussian cylinder. Why will I need a Gaussian cylinder? Because a Gaussian cylinder holds no flux. So it's not going to contribute or reduce the quantity of flux generated by that infinitely large plate. However, in the process of using this Gaussian cylinder, I have to be very careful because there are 3 conditions that must be met for it to be accurate. Number 1, the cylinder must strike the cylinder must strike the plate of infinitely large positive charges at an angle of 90 degrees. That means the cylinder should be perpendicular to the plate. That is 1. Then number 2, the cap of the cylinder must be parallel to the plate. Then number 3, the separation distance between the end point of the cylinder and the plate on the front side should be equal to the separation distance between the end point of the cylinder and the plate from the back side. So those 3 conditions must be met. Number 1, the cylinder must be at 90 degrees to the infinitely large plate. Number 2, the cap, of course, when it is at 90 degrees, automatically the cap is also at 90 degrees. So that at 0 degrees, because it's going to be parallel now. Then the next one is that the distance before and the distance after the infinitely large plate should be equal. And when that is settled, you apply Gauss Law. Gauss Law, very simple. Gauss Law states that flux is equal to Q all over E naught. And that flux is EA. And that A is the area the Gaussian surface is striking on the infinitely large plate. And because that area is circular and it takes place on both sides of the plate, you have 2A. And the area we are talking about of a circle is simply pi r squared. So you're going to be using 2 pi r squared just to get it in details. Good. So your formula for the electric field generated by an infinitely large plate of positive charges becomes E equals to sigma. Take note, you have to be very careful here. You may be wondering where sigma is coming from because we're talking about Q all over E naught just now. Don't worry, I'm coming to that. So E becomes Q all over epsilon naught A. Now, Q over A is sigma because sigma signifies surface charge density, right? So at the end of the day, your E becomes sigma all over 2 epsilon naught. Why is there going to be 2? The 2 that is coming from the 2 sides. You get it? Good. Now, if you want to calculate the force given out by this single plate, remember all positive charges radiate their force outward in the same direction with their field lines. So for me to calculate the flux given out by this, remember the formula of electric field intensity, F is equal to EQ. So if E is already sigma all over 2 epsilon naught, all I need to do is to simply multiply it by Q. And that will give me the force. And the Q we are talking about is small letter q. And that will give me the force. However, your textbook made a mistake at this point. The question was given and 2 plates were involved, but they used the formula for 1 plate to solve. However, if they actually use the 2 plates, this is what you ought to have heard. If you have 2 plates, one is positive, one is negative, we already know the electric field generated by one of the plates to be sigma all over 2 E naught. And it is facing downward. Now the negative charge that is just at the bottom radiates its own field lines inward. So it is in the same direction with the direction of the positive plate. So it's going to be algebraic sum. That will be sigma all over 2 E naught plus sigma all over 2 E naught. At the end of the day, the electric field generated by 2 parallel plates, one positive, one negative, will give you sigma all over epsilon naught. And that is for 2 parallel plates, not just for a single plate. For a single plate is half, but for 2 parallel plate is sigma all over E naught. If you now want to calculate the force, is simply the product of Q. So just multiply it by Q. And you can as well change your sigma to be Q over A, as the case may be. You get it? So basically, that is this amazing topic which you have to remember. This is chapter 3. This is Gaussian law. This is Gaussian surface. I wanted to say it's an amazing chapter, bro. Study it and you'll definitely be the best. Boom. Let's see in the next chapter, chapter 4. And that is electric potential. Boom.